And here we're talking about attractive forces well, not different actually. Attractive forces between separate molecules. So there are forces within molecules, intramolecular forces we would call those. Those are bonds, the things that actually hold the atoms together. With this, we're talking about forces that hold different molecules together. So what are the things that actually make molecules stick together to each other versus apart? And we're going to separate these into two categories: polar forces and nonpolar forces. So first we'll look at polar forces. And this is where the stuff from last week becomes important, because you need to know whether the molecule is polar or not to see if it is going to participate in these types of forces or not. Polar forces are stronger than nonpolar forces. And these work by the positive-negative type attractions that polar molecules have to each other. So two types of polar forces. First one is called dipole forces. And this is when polar molecules, which we talked about last time, a polar molecule is going to have a positive side and a negative side. And those sides can attract other molecules in that way. So let's look at, we can also review a little bit this way. Let's look at a sulfur dioxide molecule, SO2. SO2 has this kind of a shape with a single bond and a double bond. Has this kind of a structure. And let's look at whether or not that's polar. Now, if you look at the periodic table, would you expect a difference in electronegativity between sulfur and oxygen? Yeah. Remember the trends on that? Electronegativity changes going how? Which way does it get larger? That's one of the ways. So yeah, going from left to right toward F, it gets stronger. And how else? Right, so down to up toward F also gets stronger. F is the strongest, the most electronegative, so everything else kind of goes toward F. So that means if O is on top of S, O should be more electronegative than S, because that's the trend going up. And if we go back to look at that table, I think we can see that, yeah, that the difference between O and S there is about 1, which is significant in terms of electronegativity. All right, so that tells us that there is an electronegativity difference between S and O, which means each one of these bonds is going to have some negative down on oxygen and some positive up on sulfur. Negative on oxygen, positive on sulfur. And much like, I'll draw these out of the way a little bit, much like water, that means that we can separate this molecule into two poles, a positive side and a negative side. So when sulfur dioxide molecules get with each other, they can orient themselves in this particular way. So you can have one molecule that has positive and negative here connect to maybe another molecule You see how the negative and positive get close to each other there? And that can continue, that can propagate over many of these. Same kind of thing. So you have these kind of attractions going on there. And those are known as dipole-dipole forces. Now these are not as strong as bonds, not nearly as strong as bonds, but they exist to kind of hold these things together. So in a liquid or a solid state, this molecule will line up in such a way. In a gas, there are no intermolecular forces, or at least they're not very strong. So we don't usually talk about them. But in condensed states, liquids and solids, that's when these things come together in this way. So that also means, this is an important thing to remember, that when we boil a substance, when it goes from a liquid to a gas, we're not breaking any of the bonds inside the molecule. We're just breaking these kinds of things and separating the molecules from each other. The molecules stay intact. When you boil water, it doesn't split up into hydrogen and oxygen. It stays water, but the molecules separate from one another. And we see these types of forces with any kind of polar molecule. So these types of forces exist in all polar molecules. That's why what we did last week is so important in determining this. Once you've figured out whether a molecule is polar or not, then you can determine what type of forces it has. The second type of polar force is a special kind of dipole force with a very confusing name that's called hydrogen bonding. Now that's really confusing because it sounds like hydrogen bonding to something, but it's not a bond. It's not a covalent bond. It's another one of these forces. So really it should be called, I don't know, hydrogen forces or something like that. But they call it this, so we have to call it that. So don't be confused. We can say it's not really a bond. It's a type of bond, but it's not a covalent bond. It's not a covalent bond. It's another type of polar interaction, polar attraction. And hydrogen bonding are the same as dipole forces, but they only occur with NH, OH, and FH bonds. So a molecule has to have at least one of those kinds of bonds to do hydrogen bonding. And the special thing about hydrogen bonding is that hydrogen bonding is extra strong. So where the dipole forces would hold SO2 molecules in a certain way, hydrogen bonding will hold even stronger, much, much stronger. And so what's kind of the classic example of a compound that you think might do this? What's the most common thing with one of those kinds of bonds in it? Water, yeah. So this is why water has some of the special properties that it does. If we draw this here, remember water has the same shape and similar kinds of charge separation here. Remember those partial charges. And this can set up the same kind of a network. So the only real difference here is that this is extra strong. And there's some other theory about this as being something even more than just charge attraction, but we can, at this point, we can think about it in the same kind of a way. And so these things here are what are known as the hydrogen bonds. And it's an attraction that holds water molecules together very strongly, holds alcohol molecules together strongly, holds most of our biological molecules together strongly. So things like proteins, carbohydrates, all those have hydrogen bonding capabilities, which allows them to connect. So this is, for instance, why water, even though it's a very, very small molecule, has a pretty high boiling point. Any other molecule that's as small as water would not have as high of a boiling point. Something like methane, which is the same size as water. Methane is a gas, that's a natural gas. It actually takes extremely cold temperatures to liquefy methane. And that's because it doesn't have the possibility of doing these kinds of interactions. And that's the difference there. So you feel good about polar forces? Maybe? All right, well, these are the two polar forces, that's it. The last one that we're going to look at then are the nonpolar forces. Nonpolar molecules, of course, can't attract each other through positive and negative attraction because they're nonpolar, they're not polar. So what happens? How do those things stay together? We know there's some force here because things like gasoline is nonpolar, but that is a liquid, so something's holding that together. Things like waxes and saturated fats, those kinds of things are all nonpolar, yet they stay together as solids. So what's going on here? There is a type of force that works for nonpolar molecules. They are known as dispersion forces. And rather than draw it, I'm going to pull up a picture from the book. I have to plug in here before I do that. Oops, wrong chapter. Number 6. Okay. So here are these forces. This is page 197. Let's take a look at what's happening here. So you've got an atom here, a nucleus in the middle, and some electrons around the outside of it. Now there's two ways that the electrons can go around the outside of the atom. They can either be symmetrically distributed or unsymmetrically distributed. And this is happening like instantaneously. If you took a instant snapshot of an atom, either the electrons would be evenly distributed or they wouldn't be in some way. So in that very instant where the electrons are not symmetrically distributed, there is a momentary, really quick, mini little dipole. Because if all the electrons are over here, that makes this side a little more negative and this side a little more positive. And this is just for one atom. So that momentary little dipole that happens causes all the adjacent atoms, all the adjoining atoms, to basically do the same thing, to line up in the same way. So as soon as this atom that's right next to it feels a little bit of positive from this one, its electrons go over to that side, which makes another mini dipole, and does it to the next one, and the next one, and the next one. And all the atoms line up in this way, but just a little bit. And it's a really, really small effect. But it's enough of an effect that you can actually start to hold molecules together in this way. And if the overlap is big enough, they can actually be fairly strong. So you can imagine this as a size effect. Uh-oh, what was again here? size effect. Now let's just say large attractions can exist in large molecules. So the bigger the molecule, the stronger these forces are. And if the molecule is big enough, you can get some significant attraction in this way. So methane, which is nonpolar, is a really small molecule, just 1 carbon and 4 hydrogen atoms. So a small little molecule, the same molecular weight as water. And so its forces are very, very, very small compared to water. But if you take octane, which is the main ingredient in gasoline, that now has 8 carbons and 18 hydrogens, so a much larger molecule. And the boiling point of octane is about the same as water. So you can see that force starts to be large enough once you get enough atoms that can overlap and kind of see each other. All right, to compare this, we can look at some different substances and their boiling point or melting points. Grab this from the book here. Over here. So you can see ionic substances, when you have real fully charged ions attracting each other, that melting point is going to be really high because it's really hard to break those ions apart from each other. That's the strongest kind of a force. Then we've got the hydrogen bonds, which are these, what we just talked about, a type of polar force in something like water or ammonia. And those melting points are much, much lower than ionic compounds. And then if you go to the dipole interaction, so these are molecules that have a dipole but cannot hydrogen bond because they're hydrogen with other things. You see that the melting point goes down because now those forces aren't as strong. So it's easier to melt them. It's easier to break them apart. And then finally, dispersion forces, excuse me, where you have molecules that have no polarity at all. Cl2 is just Cl and Cl, so it's perfectly even sharing of electrons. Same with F and F, and now we have pretty low melting points. And melting points get a little weird with this. I'm kind of surprised the book used it because melting points don't always fit nicely in this narrative, but boiling points really do. When you talk about boiling one of these things, then you can really predict that. So if you have, well, here, let's try it. Let me show you what you might be asked to do. Here's an example from the book. Why is the melting point of H2S lower than that of H2O? Another way to word this question might be that you might see is which one has a lower melting point and why? That's something you might ask. So this one, it's telling you H2S is lower than H2O. So why? Well, here's how we go about a question like this. First, whenever we're talking about melting or boiling, we're talking about attractive forces. So whenever you see a question like this, you should think about, okay, what kind of forces are in play here? What kind of attractive forces are in play here? And so what we can do is look at those molecules and figure out what kind of forces are going on. They both have the same shape. They're both polar molecules. H2S is going to look like this. H2O looks like this. So now we want to know what are the types of forces involved in each of these molecules. Now, one of these we know. What kind of forces are involved in H2O? Yeah. So the predominant intermolecular force is H bonding. And we know that's a pretty strong force. So we would expect maybe H2S, maybe the reason that it has a lower melting point is that it doesn't have hydrogen bonding. It has one of those other forces. Is that true? Do we know? Yeah, we should figure it out. So hydrogen bonding only happens with NH, OH, and FH bonds. So we can say, okay, H2S has no OH, NH, or FH. So then it can have no hydrogen bonding. So that's part of the reason, and that would be a good reason. But let's dig a little bit further into it. What kind of forces do you think H2S has? To figure that out, we have to look back at our electronegativities and see if there's actually a polarity difference there or not. What's the difference in polarity between sulfur and hydrogen? That's what? Yeah, it's about 0.4, right? Which is pretty much nonpolar. Remember the cutoff here? We're saying anything 0.4 or below, we're really saying is nonpolar. Look at carbon. We know carbon and hydrogen is a nonpolar bond. That's the same. So carbon and sulfur have the same type of polarity there, or type of electronegativity there. So that means that this is, go back down, if that's 2.5 and this is 2.1, this is essentially nonpolar. So that means that its main forces are the relatively weak dispersion forces. So it can only have those dispersion forces, therefore that's how we can explain that melting point. So much weaker attractions between H2S molecules than H2O molecules. H2O molecules will have really strong attractions, H2S have much weaker attractions. See how that kind of works? We feel okay about that, maybe? All right, let's look at another one. Some of these questions we're skipping because we didn't talk about the shapes. So I will have to give you some of those, but let's do it anyway. We're going to take a look at this question, which I don't think is on the homework, but we can work through it together. All right, so we're going to look at the major type of attractive force, ionic bonds, dipole-dipole attractions, hydrogen bonds, and dispersion forces that occurs between particles of the following substances. So for these substances, we need to know, one, is it polar? Two, can a hydrogen bond? Or is something else going on? I think we can probably figure this out without knowing the shapes of these molecules. So does anybody take a look at all four of those? Do any of you feel good about one of them? Like that you're pretty sure what kind of forces one of those has?
Is hydrogen.
Yeah, right. So how do you know that?
Because it has 3 or 4 of them. OH, NH, and FH.
Right. So hydrogen bonds are going to be the major force in NH3. Does everybody else see that? Because we know we have NH bonds there. All right. What other ones can you see? D is ionic. How could you figure that out?
CS is a metal.
Right.
Oxide is a metal.
Yep. So that's another important part here is all the stuff we've been talking about, polar, nonpolar, this all applies to only covalent compounds, those compounds that share their electrons, and those are compounds of the non-metals, at least as far as we're talking about them now. So anything that's going to have a metal in it, some of the stuff over on the left, has ionic forces. It doesn't involve any of these other kinds of interactions. Speaking of which, how would you name that ionic compound? That's a little review of that stuff. CS is cesium. So what would you call that? Cesium oxide. Well, do you or not? That's the question, right? What kind of a metal is cesium? Does cesium have only one possible charge, or can it have some different possible charges? Just one, right? Because it's in that first column, and everything in that group 1 is only +1. So that means you were right the first time. You don't need the number because it can't have more than one possible charge. There's only one possible charge that cesium can have, and that's +1. So this one would be cesium oxide. Cesium is also sometimes spelled with an A. Like Caesar. If we did put a number there, by the way, it would be 1, because that would be cesium +1. You have oxide -2, so you need 2 + 1 cesiums there. Okay, back to the question at hand. What are the attractive forces in these others? HI and then I2. Which one? B is dispersion forces, or C? Both? B, C, C? Both are nonpolar? Yeah. Yeah, well, C certainly is nonpolar. Because if you have 2 iodine atoms, there can't be any difference in where the electrons are there. For HI, we better go back and check that chart. And so, yeah, we see 2.1 to 2.5. That's not much of a difference. So that one should be also dispersion forces. All right, so now that we've done that, let's imagine that this question asked us something else. Let's say this question asks us to rank. Let's not do that. I was going to say rank melting points, but it doesn't actually work with these compounds because they're so different in size. Normally, we would say the hydrogen bonding one is much, much stronger. It has the higher melting point. But because iodine is so big, those are actually, like I2 iodine is a solid. So that kind of throws off our trend. But that's just because NH3 is so light compared to those other ones. Size also matters here.
So this like CS3 or something. So it's only bigger than.
Yeah, and CS2O would be ionic, so those are much stronger forces. Those are ions. All right. All right, so that's all the new stuff that I want to talk about. Let's finish up with a little naming review. You may have looked through this in your homework a little bit, but we can talk about it together as well. Specify each of the following as ionic or molecular and name each. So here's what I want you to do, since we only got about 10 minutes. Take about 5 minutes and do whichever of these you can. So skip around to the ones that you really think you know. And just write down the ones that you think you're pretty sure about. And then we'll go over the ones that you skipped because you thought they were too hard in the last 5 minutes. Yeah.
If taking 7, 6 is hexagon 7.
7 is hept.
Hept.
Yeah. Well, 1 minute. All right, so which of these are you the least sure about? The one with the 7 in it? Yeah, so that's going to be a covalent compound, right? And it's going to be dichlorine heptaoxide or heptoxide. We didn't really talk about 7, but 7 is hepta. All right, let's see what else we got here. So A would be iron 2 chloride. You need to have that 2 in parentheses. B we did. What about C? Yeah, 2 is just bromine. That's elemental bromine. It's just bromine in its elemental state. That's an element. That's what it looks like. D would be calcium phosphate. No numbers because calcium only has one kind of an ion. E is phosphorus trichloride, a covalent compound. F is aluminum nitrate. Nitrate, remember, is the polyatomic ion there. And aluminum, we don't use the number because it's only +3. And then PbCl4 is lead 4 chloride. Lead can have a couple different charges, so we specify that it's 4 plus 4. And then the last one, H, is magnesium carbonate. CO3 is carbonate, Mg magnesium, and no number because magnesium is only +2. How did you do? Maybe. All right. Let's have our next quiz a week from today on naming, polar, non-polar stuff, and whatever we do Thursday. I guess we'll start getting into the mole and some more math stuff on Thursday. So
On Tuesday, do you have only naming or something else?
no, everything since the exam. So naming, polar versus non-polar, forces, and then what we do on Thursday.
And those dots also? How?
Yeah, the Lewis dots, right. Yeah. Chapter 6, and a little bit of chapter 7 that we get into on Thursday. All right, thanks everybody. I'll see you for lab tomorrow.